Today's speaker. I've been looking forward to this for some time. Today's speaker is Mike Manfra from Purdue University. He's a distinguished professor of physics and astronomy, a professor of materials engineering, and a professor of electrical and computer engineering. I assume that's because you really love going to faculty meetings.
Yeah, absolutely. Nothing better to
do. He got his PhD at BU in 1999. He was then at Bell Labs from 2001 to 2008 and has been at Purdue since 2009. He's made important contributions to various aspects of the quantum Hall effect, which is the work that I know, including the work that he's telling us about today, which is something that we've been waiting for in this field for many decades. I should take the blame. I told him that there will be many people in the audience who are not experts in quantum Hall effect. I do see, I notified some friends outside of Stanford that this exciting talk was going to be taking place, and I can see that other people are as excited about these results as I am. So we have a lot of outside experts. So I hope the outside experts will be content to have a little bit of introductory matter so that especially the students can be brought up to speed. And so without further ado, I'd like to turn over to Mike Manfra.
Okay, thanks, Steve. Thanks for inviting me and the warm introduction. I guess I need to share my screen. Let me make sure I get this working properly. Boy, Stanford, here's Stanford. Okay. Can you see my screen now, or?
Yes.
Okay, let me get this going. All right, close this down so I actually can see my own slides. Okay, let's see if this works. Well, thank you very much. I'm going to tell you about our measurements of Aharonov-Bohm interference and the direct observation of anyonic braiding statistics for the 1/3 fractional Coulomb Hall effect. And yeah, I'm Mike from Purdue Physics and Microsoft Purdue. The experiments I'm going to talk about were performed by just an outstanding supergraduate student, James Nakamura. The samples were grown in our lab by Chuang Liang and Jeff Gardner. And so the work I'm going to tell you about was published late last year and builds on some work that we did in 2019. So the topics to cover are sort of what are anyons and how do they relate to the fractional Coulomb Hall effect, the Aharonov-Bohm effect and braiding statistics in electronic Fabry-Perot interferometers, how they ideally should work and what we should expect. But then I'm going to also tell you about some of the challenges of operating real Fabry-Perot interferometers in the quantum Hall regime and how that is fairly complicated and took some changes in heterostructure device design. I'm going to tell you then about our operation in the integer quantum Hall regime, specifically at nucleus 1, to give you some confidence that the thing actually works, and then go into the fractional regime and show you our results at 1/3, and then try to convince you that we've actually seen anyonic braiding at 1/3. So in 2020, I think you could say anyons were revealed in experiments. There were a couple of experiments. The first one was a beautiful experiment done in what was called an anion collider by the French group, where they looked at current correlations in this mesoscopic device to extract the fact that they were actually observing collisions between particles that were anyons. It was a beautiful experiment and it comports with the theory as far as I can tell completely, but it's a little bit indirect. You're looking at current correlations, and so we took a little bit of a different approach. If you're going to look at anyons, it'd be nice to see sort of their defining property that they have fractional statistics, and this fractional phase is developed when you braid one of these quasi-particles around another. And if you're interested in phase and statistics, one of the easiest ways to see it is to do an interference experiment. So we tried to build an interferometer where we could sort of have direct access to the phase that develops when one quasi-particle goes around another. And so these two experiments came out last year and seem to confirm that we have fractional statistics, at least at the 1/3, the simplest Laughlin state that equals 1/3. So just to be clear, and again, I added some slides because Steve told me to introduce some of these concepts in the quantum Hall effect itself. So I apologize if this is simply everyone knows, but I'll go over it. So when I talk about statistics, I'm concerned about what happens through the many particle wave function under braiding of identical particles or exchanging particles multiple times. So as everyone knows, in 3 dimensions, we only have bosons and fermions. For bosons, of course, you exchange particles or braid them around each other, and you get the same wave function back. You get the wave function. So if you want to think of it, it's a phase factor of 2 pi. Fermions, of course, it's under exchange, you get the same wave function, but it's multiplied by a factor of -1, or phase factor of pi. And of course, this has dramatic implications for how the particles behave and what states that they can occupy, as you well know. In 2 dimensions, it can be even a little bit more complicated. It's not limited to bosons or fermions or a simple factor of 1 or -1. You can get essentially an arbitrary phase factor developing when you take one quasi-particle around another for, say, fractional quantum Hall quasi-particles. And these fractional statistics are called abelian anyons, where you can develop a phase of e to 2 pi alpha, where alpha is some rational fraction. And there's the possibility of even more complex statistics and behavior. Of course, that's for abelian anyons, it's simply a phase factor. It's a complex phase factor, but it's still the same wave function, if you will. Non-abelian particles, they can occupy a degenerate manifold of states in the ground state, and so the taking particles around each other doesn't simply develop a phase, but it corresponds to a unitary rotation within the degenerate manifold, and so you actually come into a different state. And of course, this has important implications for quantum information processing. The nu equals 5 state fractional quantum Hall effect is being pursued actively for the demonstration of non-abelian statistics, and Bob Will works on this. But potentially they could be used as a basis for building a qubit, as can topological superconductors in principle as well. So there's lots of interest in exploring not only the simplest case of anyons, which I'm going to talk about today, abelian anyons, but also non-abelian. Okay, so again, I'm going to jump to these introductory slides. I'll try to go through them quickly, but just for the students and people who aren't so familiar with the quantum Hall effect, I want to first introduce the material system. I'm talking about a 2-dimensional electron gas. And what I mean by that is I take a system, gallium arsenide and aluminum gallium arsenide, and at the hetero interface where this junction is made, there's a discontinuity in the conduction band, and basically a confining potential is established. And I can have electrons build up, and due to quantum confinement, become essentially 2-dimensional in their motion at this interface. And on the left, of course, is a cartoon, and with just little billiard balls representing the electrons. The center panel shows a stack that one of the simple stacks we might grow, where we have a gallium 100 nanometers of gallium arsenide, and then aluminum gallium arsenide, the alloy containing aluminum, which has a larger band gap and gives the conduction band offset. The electrons are built up at this interface and basically are quantum confined into subbands, and their motion is limited into 2D. So in the regime of interest in the quantum Hall regime, what we do is we turn on a large perpendicular magnetic field. Now, these electrons are free to move in the plane, but they're essentially reside in electric subbands at the interface, and so they are not free to move up and down. Now, we turn on this magnetic field, and we'll see what actually happens to their motion as a consequence of this. So the quantum Hall effect, I'm just going to give you the simplest introduction. I just tried to throw these slides together at the last minute. Occurs when we actually apply a strong magnetic field, represented here by the vector potential, to this 2D plane. So of course, the simplest term in the Hamiltonian, or there's a kinetic energy term associated with the free motion in the plane of these electrons in the presence of this vector potential. There is inevitable disorder that exists in all samples, and we have a disorder potential that goes into the Hamiltonian. And then there's electron-electron interactions, the mutual Coulomb interactions between the electrons. Now, this Coulomb potential is not needed to describe the integer quantum Hall effect, but is crucial to the fractional quantum Hall effect, and is at the origin of the fractional quantum Hall effect. But just to put everyone, give the same language, we are all talking the same language, let's just consider the non-interacting electrons, and we're just going to consider this kinetic energy term for free electron motion in a magnetic field. And this is a problem that we solve in introductory quantum mechanics. We have a sense of what this should be. If you put on a large magnetic field, these electrons start going around in circular orbits. They go in what we call cyclotron orbits. The cyclotron frequency is given by EB over MC. Here E is the charge of the electron, B is the applied magnetic field. The mass of the electron is in the denominator is the speed of light. So these little electrons, if you want to think of them semi-classically, are going around in circular orbits. Now we can solve exactly this Hamiltonian, and we can write down the eigenstates and eigenenergies. And the eigenstates, depending on basis, they'll have different representations, but the key point here is they can be labeled by two quantum numbers, n, which is the Landau level index, and k, which is represents momentum. Now the eigenenergies are given for these states by h bar omega c times n plus 1/2, where n is this Landau level index. And so the key point here is that while the eigenstates are labeled by two quantum numbers, the eigenenergies depend only on n, the Landau level index. So there's a huge, and these are called Landau levels, and due to the orbital quantization. The important point is that there's a very large degeneracy we have that gets built in and is proportional to the magnetic field. And so there's a large positional degeneracy. All these electrons on any one Landau level all have the same energy, and they can all occupy the same Landau level. And that Landau level degeneracy increases as we increase magnetic field. So if we want to I'll show you the density of states, but I wanted to first define a filling factor, nu, which basically is the ratio of the density of electrons to magnetic field times the magnetic flux quantum. It represents the number of Landau levels filled with electrons. We call that the filling factor. So if you looked at the spectrum and then you go to high enough magnetic field so that there's a large separation between the Landau levels and they have a large degeneracy, you will have this discrete spectrum. And depending on the density, we'll start filling up these Landau levels. So you can imagine if I have one electron for every state in the Landau level, I'll be at Landau level or filling fraction nu equals 1. My Fermi level will be in a gap, and this will be the regime where we see the integer quantum Hall. Of course, I could have multiple Landau levels filled, and I could even have partially filled Landau levels. And partially filled Landau levels, based on the description I've just given you, shouldn't give rise to any particularly interesting state. We have more states available than we have electrons in the system, and their state is compressible. The Fermi level, you would think, would be just in that one Landau level, so nothing interesting can happen. Of course, I wouldn't be giving this talk if that were the end of the story. So let's think about what can happen if you have partial filling of a Landau level. And of course, we learned a long time ago that if this happens at certain rational filling factors, fractional filling factors, Newton's 1/3 of being a primary example, we see what looks like the phenomena of the integer quantum Hall effect, but not at integer filling. And how do we explain this? Well, if I have 1/3, I'm at 1/3 filling, you would think I have a compressible state. It's a huge degeneracy, and there's lots of states available for the next electron to go into, and my Fermi level should be right in the compressible region. That's not what we see. And the reason we don't see that because of the electron-electron interaction, so which I completely ignored to this point. And so when we get to, say, I'm going to talk specifically about the Laughlin states right now, but very high magnetic field, we're in the lowest Landau level. So essentially the kinetic energy is not relevant anymore. There's a large spacing to the next kinetic energy level, the next Landau level, it's gapped out. All the states share the same kinetic energy. The only relevant energy scale at this point is the electron-electron interactions. And so as was originally discovered by Stormer and Sui and Gossard, this can give rise to very interesting physical transport properties, and I'll move on to that now. And of course, the explanation of this started with Bob Laughlin's seminal work in writing down trial wave functions for what the states should look like, given that they're all residing in the lowest Landau level and subject to mutual interactions. So in what we thought would have been nothing interesting, actually turns out to be one of the more interesting phenomena we've seen in quite some time. And so the fractional quantum Hall effect, as I'm going to try to describe to you now, involves exotic excitations. And what we've learned through a combination of experiment and theory is that the excitations of the fractional quantum Hall effect are emerging quasi-particles. And on the right-hand side here, I show you transport. I should again explain what this is in more detail. The black curve corresponds to the longitudinal resistance. I'm just measuring the resistance along the length of the sample. And I'll show you what a sample looks like in a second. The blue trace is the Hall resistance, basically the transverse voltage that develops as we increase the magnetic field. And these plateaus where you see quantized Hall resistance and zeros of the longitudinal resistance, lower magnetic field where I pointed out 1, 2, 3, 4, is the integer quantum Hall effect that can, as I tried to explain, can be explained simply by single particle quantization and localization. That's all that's needed. But you also see very similar phenomenology at higher magnetic field at fractional filling. And the one I'm going to talk about up around 12 Tesla, nu equals 1/3, is the large gap 1/3 fractional quantum Hall state, first seen by Sui and Stormer and explained by Laughlin. And part of this explanation, going all the way back to Bob's work, was that the excitations of the fractional quantum Hall states are emerging quasi-particles. And what do I mean by that? Well, they have some very interesting properties. These quasi-particles carry fractional charge. At nu equals 1/3, the charge associated with one of these excitations is E/3, where E is the bare electron charge. And this was recognized by Bob in his first paper. More to the point of my talk and what we're going to be talking about today in general is that it was also realized not long afterwards that these quasi-particles should obey anyonic braiding statistics, meaning they have fractional phase. And if you want to think about it, and we're thinking about just the Laughlin states, you could think about it as the Berry phase, where I take one quasi-particle and wrap it around the other. This phase that develops in the multi-particle wave function, what I call theta anion, is given by 2 pi E star over E. Again, E is the effective charge, E is the quasi-particles in the fractional state, and E is the bare electron charge. And so that's, so at nu equals 1/3, we would expect theta anion to be 2 pi over 3. And this was the work of many people over many years, but first discussed by Bert Halperin in '84 and Everos, Schiefer, and Wilczek shortly thereafter. And Steve Gilson has made important contributions to this area as well. He did, and actually one of the first proposals to try to probe the fractional statistics, I think, was by Steve back in 1990. So from the theorist point of view, I had a conversation with Steve about this a little bit earlier. You could say, well, the fractional charge and anyonic statistics are, sort of imposed upon us by the observation of the quantized plateau at fractional filling. But that may or may not be correct, but certainly it's not a direct experimental probe of these properties. And it's taken quite some time to see both of these effects, both the fractional charge and now in 2020, the anyonic phase. And you could say, well, what's the big deal? What's the problem? And that's what I'm going to try to describe to you now as the subject of our work. So, okay, let me move on. This was actually an interesting question Cam asked me earlier. So, aren't you just measuring AB in a quantum dot, and why is it taking so long? And I'm going to try to explain to you why it's taken so long, and some of the things that had to take place along the way, both in our learning and understanding, and changes in device design and heterostructure design, in order to finally see something. One point I do want to make is that one of the key enabling technologies in this area is MBE, and we have really fine control over MBE of gallium arsenide, aluminum gallium arsenide heterostructures at this point. And what's been particularly helpful for us is that in my lab, we actually do the MBE growth as well as the device fab and the measurements. And so that gives us a level of feedback or control that is just really beneficial for this type of work. And in particular, what I want to emphasize is that this enables new device designs or playing around with structures and devices with topological phases. And we have, by now, it's been developed by many people over many years, really good control over how we grow these heterostructures. And I'll just show you an example. This is not relevant for this talk, but it gives you some sense of what we can do in MBE. Here is some quantum Hall data in the n equals 1 Landau level. And this is for the experts, showing the existence of and strength of the 5/2 and 12/5 and 7/3 and 8/3 states that are available to us and are exposed at low temperature in transport. And one of the things that's really nice about the system is we can make it very clean. In my system, we can get over 35 million. My mentor and colleague, Lauren Pfeiffer, has recently reported even higher mobilities. And so the cleanliness of this system is really an enabling feature, but also the ability to tailor the heterostructures for a specific experiment. And that's is not going to be the mobility that's been crucial to our experiments. It's the ability to form heterostructures exactly in the manner we want. So let's move on to electronic Fabry-Perot interferometry and how it works in the quantum Hall regime. And so here in the left, I show you a picture of where the blue area is supposed to represent the surface of the semiconductor. You can think of it as a 2-dig. The yellow rectangles are the surface gates that we use to define the interference path, and we have source and drain contact. So these surface gates define the electronic interference path. And as you know, as well as I should make more clear, that in the quantum Hall regime, under the application of high magnetic field, current is carried by chiral edge modes. These chiral edge modes circulate around the perimeter of the sample along its edge. But we have these gates, and we build in these quantum point contacts, and they act as basically beam splitters, if you're thinking this is in sort of analog to optical Fabry-Perot interferometer. And the electron beam, the edge state, comes into this QPC. It's partially reflected, but mostly transmitted, circulates around the interferometer. It hits a second QPC, where again, this edge state is partially reflected, and partially transmitted and exits through the drain contact. And of course, this the second partially reflected beam circulates around the Fabry-Perot defined by the gates and can recombine with the current that was scattered at the first QPC. And if we think about what the current will look like through the system, it will of course depend on the amplitude of the reflection coefficient at each individual QPC, actually the amplitude square. But then there'll also be the crucial cross term, if you will, that depends on both the amplitude of the reflection coefficient, but also cosine theta. And what is cosine theta? Well, this is the phase that develops between the two returning current paths, the one that circulates around the interferometer and the one that was scattered originally at the first QPC. And if we're thinking about simple electrons in the non-interacting picture, say the integer quantum Hall effect, what would theta be? What is this phase angle that develops between them? Well, it'd be nothing but the Aharonov-Bohm phase, where this theta is 2 pi A over B divided by phi naught. Phi naught again is the magnetic flux quantum, H over E. And A is the area, the enclosed area by the interfering path within the interferometer, and B is the applied magnetic field. And of course, we can operate this device by changing gate potentials or the magnetic field that we apply. Now, that's what you should expect in the integer quantum Hall effect. If the system is completely inert, the device is behaving in the simplest way possible. What could happen if we go to the fractional quantum Hall regime? And that's where the story becomes a little bit more interesting, and I'm going to try to describe to you now. So we can measure this interference, of course, by measuring the electrical conductance across the device. We tune or change the angle by changing the area. That's by gate voltage, or we change the flux through changing the magnetic field. And so what we might expect in this integer quantum Hall regime, as our theorist friends will tell us, is lines of constant phase having negative slope in the BVG plane. So if I actually were to plot out what the expectation is, again, in this very simple picture of what an interferometer should do for non-interacting electrons in the integer quantum Hall effect, this are lines of constant phase having negative slope in what I call the delta V, delta B plane. And so these are called pajama stripes or a pajama plot, and is been worked out theoretically and also seen experimentally. And there's been lots of work on this. The reference I sort of take and use frequently is Burt's and co-workers from 2011, but there are many papers describing how these things should work, and going back to 97, where Steve was a co-author, we're describing some of how the original interferometry should work in the quantum Hall regime. Now, what becomes interesting is what happens to this phase, this angle, when you move into the fractional regime. So there's going to be a couple effects, actually. One is that the AB contribution is scaled by the effective charge. Basically, the periodicity, the AB periodicity, will change from phi naught to, in case of nu equals 1/3, say 3 phi naught, basically whatever the fractional charge is of that particular state. But interestingly, there's a contribution that comes about because of the anyonic phase of the quasi-particles. And specifically, if there are localized quasi-particles within the interferometer, the circulating current, the edge state, has a contribution to the phase it develops that is given by the number of localized quasi-particles times the anyonic phase. So this phase that develops and can be measured in principle in such a device gives you direct access, a direct measure of this anyonic phase. In particular, not what you should see is anytime the number of localized particles changes within the interferometer, which should of course change discretely, you should see phase slips associated with this, or what we call Aharonov-Bohm pattern, associated with the introduction or removal of a quasi-particle. And that phase slip will give you, or the magnitude of the phase slip will give you the anyonic phase. And so that's what we're after. We're looking for patterns that give us in the B delta V plane, this AB pattern that you see, or the theoretical expectation here, and punctuated by discrete slips that can tell us about what the actual anyonic phase is. And so that's the ideal, that's what we're after. So keep that in mind as I get into the nitty gritty and sort of the details of why that's hard. But this is what we're after. Okay, so what's the problem and what's been the problem? And this could answer Cam's question a little bit more with a little bit more detail, is you think that'd be pretty darn trivial to do and we should have done it 40 years ago or whatever it is. But it turns out that there's actually some underlying physics that makes this quite difficult and in some instances impossible to see. And that's one of these is strong bulk edge interaction. So the naive expectation or the assumption that the system is inert, the interfering edge doesn't care about the charge that's inside the interferometer is actually not quite true. So, or it can be not true under certain experimental conditions. So if you looked at a lot of these experiments, this is the naive expectation, theoretical expectation. But if you actually look at what you see, an experiment, and this is my data from my own group, so it's certainly something that we're prone or see as well, that you see lines of constant phase, sort of pajama plots, but they have the wrong slope. They're not going as you would expect for AB oscillations. They're going the wrong way. And this is what was deemed early on the regime of Coulomb-dominated oscillations. Okay, so what's going on here? How do we understand this? Well, it actually turns out that the bulk edge interactions can cause the area to change with magnetic field. So we think of this as an inert interferometer that has a fixed geometry, but that's not actually true. As I change the magnetic field, the energetics are such that the perimeter or where the interfering edge is can move around. So it can actually be true that as you increase B, the flux decreases, which is a little bit counterintuitive, but that actually can happen. And so A and B can't be controlled independently under certain circumstances. And this is a real problem because you say, okay, well, fine, I understand that now, but what's the big deal? Under certain circumstances, it makes in principle braiding unobservable because the change in the AB phase that would come about from the AB accumulation of phase that I told you about earlier is exactly canceled. The anyonic contribution is exactly canceled by this change in area. And so there's no way that it's going to work and you're going to be able to observe anyonic phase if you're in this regime where the bulk edge interaction is particularly strong and you're seeing what's called Coulomb-dominated oscillations. And it turns out, while I've called this an interferometer, these devices need to be pretty small to have high coherence. So they're actually more or less quantum dots, and there are strong Coulomb effects that must be taken into consideration. And that's been sort of the challenge. So to give you an idea of how this works, again, I added the slide just to try to make it a little bit clearer. You can be in a regime at the far left where bulk edge interactions are not important at all. And then you should see the traditional AB oscillations and see the physics you're interested in. But there can be a variety of expectations for what the patterns, the interference patterns looks like, depending on basically a ratio of parameters, what I'll call KIL to KI, where KIL parameterizes the bulk edge interaction and KI parameterizes the energy cost to add charge to the edge. And it's the balancing of these energy scales that really determines what regime you're in. And so if you're in the regime where, let's just forget the intermediate regimes, go to the far right, where this bulk edge interaction is quite strong, you can get Coulomb-dominated patterns of interference, if you will. And that's really what's been at the heart of the issue for quite some time. So again, just to emphasize, theta anion is unobservable in principle if you're in this deep Coulomb regime, which a lot of the experiments have been in because the phase change is a simple multiple of 2 pi. So I hope that makes clear why everybody's been working hard and it's taken a long time to learn this and understand it, and why progress is taking quite some time. Okay, and so to give you an example, and that clearly demonstrates this and was something we learned from, as I said, most experiments in the early days were in the CD regime, the Coulomb-dominated regime. But there was an experiment from Charlie's group, Charlie Marcus's group, where they made interferometers of 2 different sizes. And they made small devices, at the time small devices with a 2 micron square area. But they also put a metallic gate on top of the semiconductor layer. And then they made one that was very large, about 20 microns squared, again with this metallic gate. And interestingly, they saw 2 different behaviors. In the small device, they saw this Coulomb-dominated kind of oscillations, as you might, you would expect based on previous experiments. But when they went to this 2 things, where they added this metallic gate and also went to a very large device area, they did see Aharonov-Bohm oscillation, the pattern that I showed you earlier that was expected theoretically. But there's a problem. They saw this, and it's illuminating because it tells us 2 things that I'll talk about in a second. You can get into the AB regime, but if you look at the field scale at which they're probing, it's a half a Tesla. And this is very low in terms of the filling fraction. This is about nu equals 20. And the problem is this very large device wasn't very coherent. The coherency goes down as you go up in magnetic field. The oscillations were lost as you go to higher field. And essentially is because of the poor coherence. But it does teach us a couple things. One is that by going to a large device and reducing the charging energy, if you will, making a really big quantum dot, you can reduce some of these Coulomb effects. And you get that both by going to a large area, but also adding in screening layers. But the coherence is poor, and you're not going to be really able to get into a regime where you can probe even the integer effect, let alone the fractional effect. But what we learned is we need a better way to screen Coulomb interactions in order to see AB in smaller devices. We need small devices. Why? Because we want them to be coherent, but we don't like small devices because they give rise to a lot of these Coulomb charging effects. And so,
Mike, can I just ask a question? I think you said that it was coherent. He's at small fields because that's the only place where he sees the coherence effects. Why would we expect the coherence to be better at small fields than at high fields?
Several reasons, but the first being that the edge velocity is going to decrease as you increase magnetic field. So that's proportional to
it's 1 over B, right?
Yeah,
okay.
It's a U over B. So if you want to think of it that way, it's just the edge velocity is getting smaller and smaller.
I see.
And also, yeah, where the edge is in E, what potential gradient, what electric field gradient it's seeing, of course, depends on where you are in filling as well. And all those things conspire against you.
I see.
But just think of it as velocity, right? It's getting slower.
Yeah.
The modes are getting slower.
Yeah. So you need to maintain coherence longer.
Yeah. So if I have a smaller path length for a given velocity, things are just easier to observe.
Yeah.
That's the simple-minded way of explaining it. We could go into more detail, but I probably not now. Okay, but you get the point here. We want the things to be small because we want them to be highly coherent, but we need to reduce these Coulomb charging effects. That means big devices or screening layers. And what we learned here is, well, Charlie has a gate, but it's kind of far away. So what can we do? And as I said, we have this MBE system. And so you can think about it, okay, that was ex situ fabrication, putting a metallic gate on top of the semiconductor. Why don't we just build in the metallic gate into the heterostructure itself? And we can put it not arbitrarily, but pretty darn close to the quantum well that we want to probe the transport in. So on the left-hand side, I show you the stack. That 30 nanometer blue region, gallium arsenide, that's the principal quantum well, the one we want to look at our transport in and interference. But 25 nanometers away, above and below that well, we built in second quantum wells, what we call screening wells. And here we put in high density, highly mobile electron gases that are 25 nanometers away from the principal well. And of course, at 25 nanometers, the screening can be very, very strong, and we can really suppress some of these Coulomb effects. Now, as you see, that if you look at panel B in the middle, the density of the primary quantum well, the one I'm interested in, is actually substantially lower than the density in the screening well. So these are basically metal sheets really close by the primary quantum well in the two-dimensional electron gas. Now that's cool and everything because you can screen, but it makes a mess of transport, right? If you actually just put some contacts on this thing, you can't contact them separately. At least we can't. You get massive parallel transport and if you looked at the bulk transport. Yes. So that means we have to go to a modified device design, and that's shown in schematically in panel C. And that means we have to be able to isolate the transport through the central quantum well, which we want to probe, but remove the transport signal from the screening wells. And that takes a series of gates, which I'll show you right now. So we built what we just call a top and back gated interferometer. And so there's a couple things we do. We just anneal in our contacts that contact in parallel all three channels, and there's nothing we can do about that. But we do a couple of things. We thin down the sample so it's only about 50 microns in total, and then we do lithography on the front and back side to have gates that can isolate the screening wells from the quantum well and the contact. So we need a way to eliminate parallel conduction through the screening wells. And here we just completely borrowed a technique that was developed in the 90s by Jim Eisenstein and coworkers at Bell Labs to study closely spaced bilayers, where completely different physics they're interested in, but the technique works perfectly well for our tri-layer system as well. So if you apply a gate voltage around the ohmic to the top surface, you can deplete the screening well. And if you apply a gate voltage to a voltage to the gates around the contact using gates on the bottom, you can isolate the bottom screening well. And so that's what we actually do, so that transport takes place only through the primary quantum well. And you see on the left these series of gates that are on both the top and the bottom that go around the ohmics, and those are used to provide the isolation. Of course, our device is the tiny little thing on the top of the mesa. Sorry, I don't have the arrow pointing to it, but that in the center of the mesa, it's far away from any of these gates, and it sees the full potential of the screening layers. And so we get the benefit of screening without the mess of the complications that would be seen in transport. So just to give you an idea how this works, if you just measure the transport through the bulk and don't deplete any of these screening wells around the contacts, here's the Hall trace, and it gives you a very high density. It's also messy. You can't see the states. That's because there's different densities in the different wells, and so they're quantized at different values of magnetic field. I apply a gate voltage so that I have the quantum well and only one screening well, and it gets a little better. The density goes down as we expect, but there's still kind of messy transport. But then I apply voltages to both the top and the bottom of the sample, and you see the density only in the primary quantum well, and you see a nice quantization of the Hall plateaus, both at integer and fractional filling. So this technique really works like a charm. We can probe transport through the central well, the one we're interested in, and do interference experiments without the complications of the screening wells, but we still have the advantage of very good screening in the region of the device, of the mesoscopic device. So what that allows us to do is build this tiny interferometer that wouldn't have been possible otherwise. And to give you a sense, the scale of the devices we were looking at before were 2 and 20 micron square area. The first one, this is from our 2019 paper, which was still pretty big, was sub-micron squared area, and the coherence is improved. And for other fine points is that we think the screening wells actually promote much steeper confining potentials at the edge. And again, this serves two purposes. It increases the edge state velocity, which contributes to coherence in addition to also being in a smaller device. But it also is a way to limit edge state reconstruction. For the experts in the audience, you can have complicated reconstructions of the edge states from what is naively expected. This has been seen in a lot of Aharonov-Bohm's experiments that really muck up the experiment and make it hard to interpret. So these screening wells serve multiple purposes, and one of them being that it makes the edge potential very sharp and allows us to avoid edge state reconstructions. Okay, so let me convince you that this actually works. So how do you, sorry, go ahead.
Sorry, stupid question on the previous. So you're depleting this top screening layer. Your quantum point contact is actually your gate depleting the top screening layer and then into the 2-deg you care about?
Okay, I went over this way too fast, and that's my fault. I apologize. There's lots of gates, way too many gates on this sample. Some of them are used to deplete the screening wells in order to limit what the voltage probes see, right, by cutting them off. In addition, you're absolutely right. I have to, in the center of the mesa, of course, where the device is in the interferometer, I have to first punch through the screening well because it's in the way and with the QPCs. And then I also use the QPC to further define the transmission of what edge mode and with what reflection coefficient I want in the primary quantum well as well. I hope that clarifies a little. Yeah. Okay.
Thanks.
Yeah, and so some of the gates they serve different purposes, but the ones you're looking at in the center panel of this particular view graph do correspond to defining the interferometer path and are used to tune the couplings. And so those are tuning the, if you will, the potential that's seen by the primary two-dimensional electron gas. Okay, yeah, I'm running through this too fast, so please stop me if I say something stupid or it's not clear. So just to show you that this actually, these screening wells work, and we're suppressing Coulomb charging effects. As I said, these I call them interferometers, but I could call them quantum dots as well. So let's operate this as a quantum dot. And first I'm gonna build the exact same interferometer, but on a heterostructure that doesn't have the screening wells. And what do I mean by operating as a quantum dot? Well, it has the same area, but I pinched down those QPCs so they're not, and I'm working at zero magnetic field here, I should say first. I'm not sort of they're not at high transmission, they're at low transmission. So I'm actually tunnel coupling between the ohmic leads and this quantum dot object. And therefore, there's a charging energy associated with this small area device and the capacitance associated with it, and putting charge on costs energy. So I can characterize basically the Coulomb interactions by measuring Coulomb blockade at B equals 0, and the height of the by doing differential conductance measurement. So I'm applying a finite source drain bias. That's the y-axis. I change the gate potential to change basically the size of the dot, if you will, and I map out the conductance as a function of these parameters. And it's well known, this is standard physics from quantum dot physics that's been explored for many years, that there'll be regions where you're coupling to either excited state, but there'll also be regions where you're because of this Coulomb effect, you're not able to move charge onto the quantum dot until you'll develop these Coulomb diamonds. And they give a characteristic charging energy, basically E squared over 2c, the capacitance of the object of the quantum dot. And so if I build the exact same interferometer, but I do it on a standard heterostructure without these screening wells, I see classic quantum dot behavior. You see these large, nicely formed Coulomb diamonds. I can measure the height and tell you the energy scale is about 200 micro EV for charging these. I can see excited states. I'm basically doing 1990s quantum dot physics. Now I take the exact same heterostructure and put it on, I take the exact same interferometer design and put it on a sample with screening wells, and I see a dramatic reduction of the charging energy. Actually, it's kind of hard to resolve these Coulomb diamonds. And so there's at least a factor of 10 reduction in the Coulomb charging energy simply by adding these screening layers for the exact same device geometry, if you will. So that it's a way of calibrating that is actually working and doing it by not in the quantum Hall regime, but B equals 0. And so that's an indication that the screening wells are doing what we think they should be doing. Okay, again, I'll mention this for the experts. We can gloss over it. The screening wells also provide a sharper confining potential. And this is supported by simulations we did back in 2018 to trying to figure out if this would work at all. So now what I'm showing you here is just a single QPC trace. I'm not using an interferometer, I'm just looking at the QPC at nu equals 1. And we have quantized conduct. This is the trace on the top, the red line where we have quantized conductance passing the one edge mode. And then there's a sharp cutoff. The conductance drops very cleanly and very sharply as a function of gate voltage to 0. That can be contrasted with what's been seen before. This is again at nu equals 1, some data from the Aharonov-Bohm group, where you see the change in conductance from 1 unit of quantum conductance, or very gradual and slow reduction, and even there's some resonances, and then there's even potentially a quantization at 1/3, even though he's at, supposed to be at the 1 nu equals 1 state. And what we think this is all related to the sharpness of the edge potential and surface, edge state reconstruction. And that with a soft confining potential, you're susceptible to this, and certainly in the fractional quantum Hall regime, it's a big issue and a problem. So the sharper we can make the confining potential, the better chance we have of avoiding reconstructions and having the simplest edge state as possible. And it will still be complicated at certain fractional states, but we're trying to avoid some of these complications that come about because of the non-ideality of the confining potential. So that's a detail, but it does seem to help. Okay, so let's jump right into operating as an interferometer, and I'm going to go to nu equals 1. And here you see what looks like AB oscillations, and when we have the magnetic field versus gate voltage plot as a function of these two parameters. Now, just note that we're already at 4.5 Tesla for these scans, so we're at relatively high magnetic field. You see very strong oscillations. I'll talk about their temperature dependence in a second, but they have the right slope. They're very visible, so that's really nice. And the idea is that this is done in a device that's 20 times smaller that's been done before with these surface gates, and that is what gives us the high coherence and the ability to see these things. We're operating in the AB regime, in which historically would have been deep into the Coulomb dominated regime because of the smallness of the device. And so the interference is large amplitude and robust. It survives up to hundreds of millikelvin. We can quantify that by a coherency factor, which basically looks at the temperature dependence of the K of the oscillations, and the temperature scale is 200 millikelvin, which is nice because these things are just darn easy to see and they last to high temperature and all that sort of good stuff. So this was good confirmation that the device design was working in principle, but it is in the integer regime and perhaps not so interesting. There's no anyonic phase to be seen here. You see that just the standard Aharonov-Bohm effect. But anyway, we're working in a device that's very small, so we hope we have a chance of seeing something in the fractions as well because of this high coherency. So let's take this right up to 13 Tesla and go to nu equals 1/3. And here, I've just tuned the magnetic field. We're up at 13 Tesla, and I won't go into the details or how this is all extracted, but suffice it to say, first of all, we see the correct slope to the interference signal. It's not Coulomb dominated, It has the negative slope to lines of constant phase. We're in the AB regime. If we look at the periodicities, both the gate voltage to periodicity, the magnetic field to periodicity, and we do the proper scaling from what we have seen in the integer effects in the integer regime, and what we know about how the area changes as a function of gate voltage, this is completely consistent with AB oscillations of fractionally charged quasi-particles, E/3 as the charge. And this is from our work in 2019, the first paper where we showed that the device could work. Now,
Mike, wait, one other question. So just, you said this is small, but so how many flux quanta are through the interferometer? What are we?
Oh, now you're gonna make
That's still a huge number, isn't it?
Yeah. That's still a huge number. And I'm trying to remember what the effective area was. I'll look it up and tell you afterwards. Can I do that?
Yeah.
To
Okay,
figure
but
out
it's,
exactly, but it's not a few.
It's hundreds
It's not
or
a few.
thousands. It's not a few.
That's right.
Okay.
It's not, but I don't remember exactly.
Okay.
My point is here that we can see AB oscillations, but on the other hand, you might say, well, okay, that's cool, but it's a little disappointing in a way, right? I see AB, but I told you, and it's consistent with the charge of 1/3, but the charge at nu equals 1/3 had already been measured by shot noise experiments. So I'm not telling you anything you don't already know. And I don't see the discrete phase jumps that I told you in the simple theoretical model I should see. And so you can say, well, it's cool, it's a device innovation, but it doesn't tell me that much new. And that's true. And we had to understand why and make modifications from there. And in hindsight, it actually turns out it's completely understandable. It's actually what we should see, or at least what the theorists tell us we should see. And I'll explain why now. I do want you to note the magnetic field scale that I plot. It's very small. It's, basically whatever it is, 50 millitesla wide for this plot. And we're operating over a very narrow or relatively narrow range of magnetic field for practical reasons. And that is associated with device stability and the range over which we can sweep and have the device be stable. And that has to do with where we are in magnetic field and the density that we're operating at. So that means we can only probe in this particular device in heterostructure over a limited range. But there's also a good reason we don't see the discrete phase slips over this range and in this device. And that's because we've overcooked a good thing. We've introduced this screening, but this screening actually suppresses the formation of quasi-particles, at least over a limited range of magnetic field, and keeps us at constant filling. And so there's never going to be a quasi-particle entering or leaving the device, at least over a very limited range. And all we'll see is the AB contribution. So let me try to explain that a little bit. What we learned from Bert Rosenauer and Adi Stern. So there's analysis that basically says, do you stay at fixed filling factor or do you stay at fixed density? And this is determined by a competition of energy comparison of energy scales. There's a competition between the energy cost to create a quasi-particle, say I stay at fixed density and the filling factor changes, and the electrostatic cost to keep nu fixed. What I mean by that is that, okay, we change the magnetic field, but we could also add extra charge to the device, so that the device, or the two-dimensional electron gas stays at exactly 1/3 filling. And of course, what I did was added in these screening layers just for that purpose, to reduce this charging energy, to make it easy to add charge on and off the dot, if you will. And so that's not benefit or is working against us in trying to see the phase slips, which come about because of the introduction rather of these quasi-particles. So you can imagine if your B0 is sort of the center of the nu equals 1/3 plateau, you'll be in a regime where all you see is AB oscillations without any phase slips with 3 phi naught periodicity, because what you're actually doing is just staying at fixed filling. It's always at 1/3, at least over a narrow enough range. Of course, as you add more and more charge to the device, that comes at an energy cost, you pay a penalty. So eventually there'll be some critical magnetic field where a transition takes place, where you actually go from being at fixed filling to being at fixed density. And so you can imagine, just in a simple cartoon picture, I'm at the center of the gap with the Fermi energy in the middle of the gap where the density of states is low. I can just add, I'm adding charge. As I move further and further in the magnetic field, there'll become a point where it's energetically favorable to create quasi-particles rather than charge up the dot. And so if I go either way off the center of the plateau, I should eventually see some sort of transition. But of course, in the device I had, I operated over a very narrow range, and I wouldn't expect to see this. So indeed, you can actually calculate what you might expect for this range of magnetic field over which things stay relatively constant. And there's a simple formula, I won't go into it, depends basically on the ratio of the quasi-particle formation energy and the charging energy associated with the device. And the interesting thing, if you do this for the device we just showed you, the range would be hundreds of millitesla, not where you say fixed filling, not 50 millitesla. But this obviously points us now in, after Bert and Adi tell me what to do. I want to go to lower density and I want to go to a smaller device. And that's the experiments from last year that get us to braiding. So we do two things. We make the device smaller, which boosts up the charging energy, not so much that we get in the Coulomb dominated regime, but certainly increases the charging energy. And we reduce the 2-deg density in the heterostructure. That means we're working with a new heterostructure. And that does two things. We get to a lower density, smaller device. So the smaller interferometer, even the lithographic area for this new one is 1 by 1 micron. So the effective area is quite small. And I've reduced the density fairly substantially. And what that means is I can apply lower gate voltages, which is for the experts and everyone who does this sort of mesoscopic stuff, enhances the device stability. Basically, I don't have to bias the thing as hard. It's very stable for operation, and I can operate it over a very large magnetic field range. So I can operate it by really probing over a broad range of the nu equals 1/3 plateau. And that was very helpful. So let's look at the interference in this new device and new heterostructure.
I have a quick question, Mike. As you lower the density, don't you have a problem with disorder? That the effects of disorder become more important?
Wow, it was growing in my machine, Eduardo, so no. Yes, absolutely. Yes, that is a very good question and a concern. And what I'm going to say is, and it is certainly a concern as I go to the more fragile fractional states. So one of my concerns about trying to do this at 5/2.
Right.
Now, I'm looking at just a primary Laughlin state at 1/3, where it has a huge gap, and it's the easiest to see. So even this is not, and as I alluded to, but didn't say specifically, is not 30 million mobility in the end, but it is still several million mobility. I don't remember exactly, to tell you the truth. But disorder is more of a problem at lower density and something that we have to consider, but it's good enough for what we, at least for the fractions we're looking at right now. Whether it's good enough later on for more exotic physics, I don't know yet, or if I'm going to be able to build a device like that. So to look at 1/3 and primary Laughlins and maybe some hierarchical states, this is going to work fine. Whether I'm going to be able to do anything for non-abelian states with this kind of structure, I have no idea yet. It's going to be hard. I hope that answered. I was being snarky,
Yes,
but so this disorder is certainly an issue. Sometimes it can help you, but it will be a problem later on. So let's look at the interference pattern and this new device and new heterostructure. And remember way back when I told you about the phase that should be accumulated if you're looking in the fractional regime, where you have AB contributions and anyonic contributions. The AB contribution will be scaled by the effective charge, but we should also see a contribution in the phase to the phase that's developed in the interferometer from the anyonic phase and any changes in the localized quasi-particle number. And here you see the pattern, but again, we're not only at lower magnetic field, we explore a much broader range. we're going to explore a much broader range even than that later on. But in this, you see the lines of negative slope with constant phase with negative slope, doing just like we hope for AB type oscillations. But now we see some discrete jumps, glitches in the data. And these glitches, I'm going to argue, are associated with changes in the quasi-particle number and the accumulation of the anyonic phase. So how do I do that? Well, let's fit the conduct. There's many ways of analyzing this, and we've done it many ways that are all consistent among the different fitting mechanisms, but I'll tell you the simplest one. We take the conductance and fit it between the jumps to the formula I show you here. Basically, that there's an AB evolution with a fixed offset, and then we fit it. So here are the sorry, I didn't tell you where the discrete jumps are. There they are. So where I put the dotted lines, but in between these dotted lines, what I'm going to do now is fit the conductance, assuming we're looking at just AB evolution. Okay, so I fit those lines and do least squared fits to the data, and then we're going to do it in the different regimes, basically before and after the jump, to get the phase jump. What's delta? So delta theta. And if we do this, and you look at the various phase slips, and you calculate what the jump is, they all turn out to be very close to what we expect for 2 pi over 3 phase, anyonic phase. So here are the values that we will extract, and you can see at the top, they vary a little bit, but and there's reasons why they should. But if you look at them and take the average, what you see is delta theta is minus 2 pi times 0.31 plus or minus within the limit of our accuracy of fitting this to 0.04. And of course, theory tells us that theta anion for the 1/3 state should be 2 pi over 3. This is, as an experimentalist, I consider this pretty darn close and repeatable, and I'll show you that in a minute. So we take this as confirmation that these phase jumps are actually due to the anionic contribution from the localized anions within the interferometer. And so this is the upshot. Everything else will be confirmational, but this is really what we were looking for. And the closeness of the value that we extract to theory and its reproducibility gives us a fairly high level of confidence that we're actually looking at an observation of anionic phase. Okay, so how do we explain these discrete jumps? If you just take a simple-minded picture, near the center of the plateau, we should be in a regime that's where in the middle of the gap, the density of states is small, but and again, this may be associated with the disorder that Eduardo was referring to. There could still be some localized states for a particular configuration of voltage and magnetic field where it's energetically favorable to create a quasi-particle or remove a quasi-particle in the case when we're increasing the magnetic field. And so this is how we understand the formation of these discrete jumps with near the center of the plateau, where we're in the center of what you would call the AB regime. Okay, so I said that this device is much more stable and I can operate it over an even larger regime. Let's look at the data in an expanded regime. But before I get to that, I want to show you the reproducibility of these discrete phase jumps. And so these are 2 scans of the same device taken back to back, but there's an hour between the scans. And the discrete phase jumps are located in almost exactly the same magnetic field and gate voltage values. We get similar extracted values for delta theta for each jump. There aren't just some random glitches or something like that changes every time you look at it. Not only that, we've looked at it in multiple devices and in multiple wafers now, and all the data we have, at least till now, is consistent with this interpretation and repeats this basic observation. So this is a reproducible and systematically observed effect, all yielding a anyonic phase for 1/3 of 2 pi over 3. So we have a relative, we could always be wrong, something or misinterpreted. That's always a possibility, but we have, to the best of our ability, tried to reproduce it on different devices and different heterostructures, and everything checks out so far. But let's look at the data over even broader range. And now I'm going from 8.5 Tesla to 9.3 Tesla. And this is, we're sweeping over a broad range of the quantum Hall plateau. And remember, our theorists, colleagues, Stern and Rosenau, told us that we should see some sort of transition occur. Well, we do see a transition, not exactly what you might expect, but I think we can understand a lot of this. So in the central region around the center of the plateau, which is marked by these dotted lines, we see this AB behavior punctuated again by the discrete phase slips. But then as we move to both higher magnetic field and lower magnetic field, further away from the center of the plateau, we see a transition. The lines of constant phase flatten out, and there is a finite width in magnetic field to this region over where we see the pure AB type oscillations. Now you measure that, and it's about 450 millitesla. As I said, Stern and Rosenauer told us there's a way to predict or calculate what this range should be. And if you do the calculation, which also includes a measure of the quasi-particle formation energy, which we measure by measuring the bulk gap, 5.5 Kelvin, the range of which theory tells us it should be in this regime is about 530 millitesla. We measure 450. Yeah, not so bad for an experiment, I think. And we do see a transition. Now, so the width of the central region is close to the value predicted by Rosenauer and Stern. The lines of constant phase flatten out, as is also part of the prediction. But what we don't see is the clear change in periodicity. We don't see the phase slips going from 3 phi naught to phi naught in the high and low field regime. And the question is, why don't we see that? And I think we understand that, and I'm going to show you even more data on a newer device where we do see it, and I think it's all self-consistent. So if you look at the thermal
sorry, Mike, what was delta in that previous? What does delta mean?
The energy
5.5 Kelvin.
Oh yeah, I'm sorry, I didn't even stop to say that. It's the energy gap of the bulk gap, the formation of quasi-particles in the 1/3 state. So if you measure activated, say you look at the plot on the lower left, which has the longitudinal resistance and the Hall resistance, and you look at the activated transport. What we call, at least as experimentalists, what we call the gap is the extracted from the exponential dependence of that resistance on temperature or inverse temperature. And that's called, by experimentalists, maybe not by theorists, but is called the gap. And that's the best measure we have, and it's been used just throughout the history of the field for quantifying what the energy scale is for creating quasi-particles in the bulk.
Got it.
And so that's delta in that case. I should be clear. Thank you for pointing that out. So, but that's that.
May I ask a question? Does this tell you something about some semi-classical size of the quasi-particle?
Let me think. I know what the magnetic length is at this field scale. It's on the order of 9 nanometers or something. What else I can extract? I'm not sure. Are you asking me how many, the number of electrons that are involved in the formation of a quasi-particle, or I'm not sure exactly.
I was just wondering whether the length scale of the anion merely has to be smaller than the size of your system, or smaller than.
Yeah, presumably that's the case.
Lambda radius, just or.
Yeah. So so the magnetic length, I can tell you, which is the length scale for the individual orbitals, of course, is about 9 nanometers at this field. And that, of course, is much smaller than any of the, at least right now, at the dimensions of the device. So these are, if you want well localized and identifiable quasi-particles within a larger object, and presumably not, you know, at the edge or anything like that. That's all I can tell you right now. But that's the length scale, basically 10 nanometers. And you can compare that to any relevant length scale of the device that you want. And then, you know, this is not anything we have to worry about, that the device size is on the order of the anion size, and you have to worry about, you know, you're looking at those sorts of complications at this point, at least.
Okay, thanks.
Yeah, good. Okay. But now let's look at the thermal decay. And again, I'm assuming everybody knows this and it's wrong of me, but let's look at how these oscillations in the various regimes of magnetic field change with temperature. And for people who do quantum Hall physics, you know, there's characteristic energy scales. These things depend essentially exponentially on temperature. And so if we look at the decay of the oscillations in the three regimes, the central region, and the high field region, the low field region, what we find are vastly, it's all reasonably well described by exponential activated behavior, but vastly different temperature scales. So in the central region, we have a temperature scale of about 94 millikelvin. In the high and low field range, experimentally, what we extract is an energy scale of about 30 millikelvin. So 3 times smaller T0, which is just the defining energy scale in these different regimes. And what it suggests is that when we go really far away from the center plateau and start creating a lot of quasi-particles, there's thermal smearing. Basically, the high quasi-particle number leads to dephasing due to thermal smearing of the quasi-particle number. And actually, this is kind of good news in some sense, because it tells us about the non-local influence of anion statistics. Basically, the interference signal, the phase, depends critically on the number of quasi-particles. And if that's changing on the time scale of the experiment, you're going to see a smeared out signal. And the fact that we see very different energy scales in the central region and as opposed to the region where we think we're creating a lot of quasi-particles, I think is fairly indicative. I will also say you can do the same experiment in the integer regime, where there are no they're just electrons, and none of this is seen. It's the same the Aharonov-Bohm behavior is seen across the full width of the plateau. And so this is very specific to being at a fractional state where we believe we have anions. And if you actually
no, what about sorry,
go ahead.
How about the temperature dependence in the integer regime? That's still the same form of temperature dependence, isn't it?
Absolutely. But what I'm saying is that there's no variation of that moving away from the center of the plateau when you create just electrons, and you don't expect any contribution to the phase that's built up in the interference signal. It should just be the AB contribution in that case. And so the temperature dependence is the, it doesn't change. There is a temperature dependence, and it's activated just as you might expect. A different scale, of course, because of different gap.
Sorry, Mike, I'm also a little bit confused. That you call this activated, but my understanding was this was e to the minus t over t naught, not t naught over t. Is that, am I confused?
Yeah, okay. I'm using these terms loosely. I apologize. Yes. Yeah, you're
yeah.
correct.
So this is not activated behavior. This is
yes, right,
from
right.
destructive interference.
That's right.
Like the temperature dependence of quantum oscillations.
I used the word wrong. I was wrong in how I said it. Absolutely.
Yeah.
But before it was more like a gap. Was it in the?
Yeah, but what before was activated behavior.
Yeah. When I was talking about this competition between quasi-particle formation and charging energy, that is what I was talking about. There is the activated transport associated with formation of quasi-particles in the gap regime. That's right.
Okay, good.
Right. I wasn't speaking precisely, and yes.
No, sorry. I just wanted to make sure I understood. Yeah.
No, you're right. You're right. Absolutely right. Thanks for clarifying. Okay, so if we look and try to simulate this, and basically as a function of temperature, the relevant scale is the temperature over the basically this EC, and you think about how many quasi-particles will be created in the different regimes excuse me, different field range at a different temperature. At a very low temperature, we'll see basically how many quasi-particles are in the system as a function of magnetic field. At very low temperature, of course, it'll be discrete, which changes with the number of flux quanta that go through the system. And you would see the plot A on the left, where you have the pure AB regime with the 3 phi naught periodicity. I show you. And then you go into the quasi-hole regime at high field and the quasi-particle regime at low field, where the periodicity should change to phi naught. That is because at very low temperatures, the quasi-particle number is fixed and only changing by changing the flux through the system, not random changes due to thermal fluctuations. Now, as you increase temperature, the AB oscillations, again, where we're talking about something that is determined by if you will, this ratio of gap energy, which really was the activated transport to the scale for charging, is maintained. But these quasi-particle fluctuations are rapidly damped or increase as we increase the temperature. And these fluctuations then affect the phase that's developed as by the circulating edge state and dampen the interference signal that you see. And so it's consistent, at least qualitatively, with what we actually see, meaning that in the central region, we see the AB oscillations punctuated by a few discrete phase slips. As we go to high and low magnetic field, the lines of constant phase should flatten out, but not seeing the discrete jumps associated with flux-driven changes in the quasi-particle number is actually a thermal effect. In our data, what we see is consistent with just this thermal smearing. So what does this say?
You should have dirtier samples.
Well, I have a quick question.
Yeah.
Do you see the beginning of the 2/5 state? Or this is away from the 2/5 plateau?
We're not in the 2/5 yet. I gotta.
In 1/3, but at some, there's some width to these plateaus.
Of course, yeah, and it's a good question, but as far as I remember, we're not bumping into it yet. So let me check to be completely sure, but I think we're still in the regime where we're in the 1/3 plateau.
Okay.
Yeah, I'm 99% sure, because that's what the experiment we were doing, but that is a potential issue, but we hadn't left the 1/3 regime yet. And so I'm pretty confident I can say we're not seeing effects of the 2/5 state yet. Okay, so there was a comment about, okay, I make a dirtier sample, or what do you do? Okay, so that kind of tells us what to do, actually. What we did is decrease yet again the size of the device and made a much smaller device, substantially smaller, to change these relative energy scales. And now we actually see, even at the electron temperature that we're able to achieve, our fridge temperature is about 10 millikelvin. We think the electron temperature is actually around 20 or 22 millikelvin in this particular case. We see the onset of, we see the transit, first the central region, where we see the AB punctuated by these discrete phase slips, again, which give us 2 pi over 3 as the anionic phase. So that's all nice. Again, there's another device. But then when we go to high and low field range, we actually start to see the oscillation. There's a discernible periodicity in the high field, or certainly in the high field range, what you see. And now you start to see the data looking more and more like you might expect, as Rosenau and Stern tell us, that we have this transition from a periodicity of 3 phi naught. That's the central region where delta B is about 83 millitesla. That's the periodicity. When we go to the high field regime, we go down to about 20 millitesla. So this is early days. We're just measuring this right now, but it seems like we're actually seeing a transition from 3 phi naught periodicity to phi naught periodicity. That's clearly discernible in these data sets, looking more and more like we might want. And we look at the temperature dependence, and that is again in the high and low field range where we're looking at these thermal fluctuations. We see rapid thermal smearing, while the central region where we see the anionic phase and AB contribution is less sensitive. And we see the data, if you will, if you just want to say qualitatively, in the small device at high temperature, this is 90 millikelvin in the lower panel. That looks like the data I showed from the original paper from 2020, where we do see a transition, but just a flattening out of the lines and no discernible periodicity. So now we can actually say that we think we have a fixed quasi-particle number, or more stable because of the energy scales, as we go to the high field regime, and we see these the periodicity associated with the phi naught introduction of quasi-particle introduction associated with a change in flux of phi naught. And so this is data that we're taking right now and working on and drafting a manuscript. So, but it's also encouraging in that we change the device in a way we think we should, and the physics that is expected sort of is visible. And so that is, again, helps us gain confidence in what we're doing. And but not only that, but also that the models have some validity as well to match what's seen in real data. So again, I've probably gone way over, but let me try to summarize. The key thing here was a dramatic suppression of bulk edge coupling in Fabry-Pro interferometers with screening wells. So basically, using these screening wells really makes us able to make really small interferometers that are highly coherent and therefore, and also not susceptible to these Coulomb charging effects. And that's the whole key to get this thing working. And so in 2019, we first got this idea working, and we were able to see AB oscillations at 1/3. That was nice, but not what we were really after. Then going to smaller devices and lower density, we got into this regime where you can probe it over a broad range, and we think we have direct experimental observation of anyonic braiding statistics. And now we're working with other devices and other heterostructures that seem to be consistent with sort of the finer details of what you might expect when you make transitions between different regimes. So that's where we are right now. We're certainly interested in the near term. We have other experiments going on where we actually put an antidot in the center, where we're going to try to control with electrostatic potential, in a controllable manner, add or subtract quasi-particles. And so that would be another level of control in seeing the discrete phase slips associated with tunability of the quasi-particle number. We're also looking, the next step for us, we're sort of cautious, is, okay, all we've looked at now is 1/3. 1/3 is the simplest Laughlin state with the largest gap, the simplest edge structure, you expect just one edge mode. Can this work even with hierarchical states? So let's go to 2/5. Let's see what happens at 2/5. That's on the agenda as well. And then, of course, we're thinking about potentially how this might work for non-abelian states, but I would say that's a hard problem for a lot of technical reasons. And Eduardo actually already pointed to one about how clean we can make this with all these gates and changes into the heterostructure and all of that, how clean we can make the system. So that's it. I'll take any additional questions if you have. I'm sorry for some of the confusion I generated with rushing over things or not speaking precisely, but I'll try to answer any questions you have.
Let's people can unmute themselves. Let's give a round of applause. That's a really exciting talk.
So the reason I asked you why so if you were getting closer to 2/5 is whether you were seeing some kind of compressible regime of the quasi-particles when your lines basically flatten out. Because the regime where you can measure the fractional statistics well is where the vortices are well localized, presumably.
Mhm.
So presumably at higher densities of these vortices at a given temperature, they will begin to be mobile. And I guess that's what you're measuring in that regime.
Well, but he was measuring it as a function of temperature.
As a function of temperature.
Right, but yeah, but that it's a bit like variable range hopping or something like
Yeah.
that. So in that sense, they are moving. That's what it means.
Yeah.
But at a given temperature, so it's actually more like, I know it's not correct to say it's a fluid, but at least the vortices themselves behave as an additional system in a sense that is compressible, presumably. And that's the origin of your I suppose. But
And I hear what you're saying. And okay. So, okay, what's that going to do to what we actually measure? So is your point being that in the central region where the state is actually, you're saying it's compressible in that?
no, incompressible in the central region. There are very few.
Yeah. Okay. Yeah, sorry about the central region. The central region around the center of the plateau, that's certainly true. I'm saying now at inside, you're saying the bulk is certainly still in the 1/3 state, even at those higher fields, because I can measure and I can see concurrently what the quantized Hall plateau and zero of resistance. So presumably I'm still in, at least in the bulk, I'm still in a incompressible state. But your statement now is that in the interior of the interferometer at these fields, I may be in the compressible regime. Is that, if I understand what you're saying properly?
Well, the vortex is maybe maybe like a compressible system, basically in that regime. Right? They are moving. They are not well localized anymore, perhaps. But,
And okay, I'll have to think about that. And the consequence is, I'm trying to think of what the signature in my experiment would be then.
that's where you.
Can I maybe ask a related question? So, could you imagine looking for the dynamics of the quasi-particles this way? You know, you sit there and I measure some resistance, and then some quasi-particle tunnels from outside to inside, and switches the interference. So the resistance of your interferometer will change, and maybe you could directly see the dynamics of the quasi-particle. Is that something that's...
A related thing I was going to ask Mike is that if you go right when you have the phase slip, right, that's when the quasi-particles go in and out. Like Steve is saying, okay, well, there's some dynamics. The quasi-particle at that point is going in and out. Would you see enhanced noise in your current?
Yeah.
Because
Exactly.
Okay, that is interesting and potentially true. I don't know the answer because I haven't looked at it in detail experimentally. But okay, well, let's be clear on what I think we're talking about multiple things here. I thought Steve was just talking about, you were saying charge coming in from the outside into the interior of the interferometer, or versus a quasi-particle generated within the two-dimensional electron gas that's, you know, localized within the interferometer by a change in flux. I'm a little confused of what you're saying. I'm not looking at, I don't think, dynamics of, in that case, of charge coming in from the outside. Maybe I haven't thought about it.
So what I was asking is the following. You'll sit at fixed magnetic field.
But I don't sit at,
Sit-
okay. But that's not what the experiment is. I could do something that you're going to
I'm-
describe now, but that's not what I
Just
did.
think, I understand. I'm just thinking about something different. And I
Okay,
think
very good,
that's
very
what Claudio is thinking about too. So I sit at fixed magnetic field, maybe ideally near where one of these discontinuities occur, phase jumps occur. And then I imagine that, sometimes there's a quasi-particle inside the interferometer and sometimes there isn't.
Mm-hmm.
Yeah, just as quasi-particles tunnel. I'm not exactly sure from where. The easiest thing for me to think about is from outside the constriction to inside the constriction, but maybe that's not sufficiently imaginative. But at any rate,
Okay, yeah, let's go with it. I hear what
the
you're saying.
number of quasi-particles that are enclosed is changing with time. And then since your voltage is sensitive to that, you'll see some shot noise variations in your voltage, in your current. In your current, yeah. It seems plausible. I haven't done it, and I haven't set up to do that. But it sounds like that could be true. The way I was thinking, of course, in our real experiments is that these changes in that quasi-particle number, at least in the central region, are driven by changes in flux and within the gas that's already in there, in the incompressible state. Yeah. Okay. And that's why I was a little not sure what you both and Eduardo were. Yeah, it could be the same thing. It could be just the system rearranging. But as Claudio points out, if you sit right on one of those phase jumps, you're sort of in a place where the system is on the verge of having one less or one more quasi-particle, and so you could see you might be able to see the dynamics of fluctuating between those two states.
Yeah, that sounds interesting and plausible. I haven't done it, but it could be a useful probe to think about how. Yeah. Okay. My first thing was just to see if I could at DC controllably bring in quasi-particles or not with basically the antidot in the center, and yeah, so that I could convince myself.
We're never satisfied, Mike. You do a brilliant thing.
I was like,
why don't you do?
Working. I thought it would be cool, but yeah, you have something more interesting in mind. That's good. And harder.
Hey, Mike. I was just.
Hey, Harold, how you doing? Haven't talked to you in a while.
Yeah, likewise. Don't understand any of this, but just to show that you showed at the early intro like 5/2 gap of, I don't know, like a half Kelvin, 0.6 Kelvin or something.
Yeah, that's right.
So if I understood correctly, or if I have these screening gates, all things being equal for these kind of correlated fractional states, the gap's going to go down, presumably, right? If I screen out interactions, all other things being equal. First, let me confirm that's a fair statement. And
let me think about that, because it's about what I'm screening are long-range Coulomb effects, and I haven't investigated that, how sensitive the gaps would be. You naively, yeah, I would agree with you. I'm just thinking, yeah. But
or
is
maybe
it true that it's going to be affecting the short-range interaction between the electrons that form the incompressible state? I probably need some guidance on.
Well, so maybe
that would be compared to the separation between electrons.
Yeah, and so I don't think it's actually going to be have that much effect, but I'd have to think about that. Meaning it's not just obvious that by screening these long-range potentials that I'm changing the inner electron interaction, but maybe Steve or somebody, or Claudio or someone.
But that length scale
We're
for you
changing the range of the electron-electron interaction.
Sorry, I couldn't understand or hear.
Presumably, you are changing the range of the electron-electron interaction. So you may be screening the long distance part of the interaction.
Yeah, as long as the gate,
that's what I was saying.
Yeah, as long as the gate is farther away than the separation between electrons, it shouldn't.
Yeah, then it
affect
shouldn't really
gas
matter,
storage.
right? So I don't think it's going to have that dramatic, my
Yeah.
instinct, but not
Oh, okay, so
verified or
maybe,
known, is that it's not going to have as much of an effect as you might naively think.
Right.
but I guess what I was curious about is, are things self-consistent for the fancy stuff I imagine you care about, right? Because I think you showed that
Whoa,
the
whoa, whoa, whoa. What do you mean the fancy stuff I care about? This
the
is the fancy
fancier stuff. Okay, let me say it that way. But
Hmm.
you got the Coulomb charging energy in your recent stuff down to like 20 micro EV, if I remember correctly. And so I guess
Yeah.
I'm just kind of curious about whether this path would be self-consistent in order to do interference experiments in these kind of fragile states like 5/2. Because I was kind of wondering what's gonna die first. Either that you fall out of the Aharonov-Bohm regime and going into the Coulomb charging regime, or if you're going to pull down kind of the gap scale. It
But
might be a
not, okay, I would say this is an interesting question and what I'm thinking about, but not for the reasons you're suggesting.
typical Mike answer, but okay.
You're just wrong, Harold. Sorry. No, all of those things are considerations, but I think, and I could be dead wrong, is that all other things being equal, I'm not killing the gap because of these screening wells. Or the screening that's coming about, because I think I'm primarily affecting the long range part of the Coulomb potential and not at 5 or 10 nanometers. I am doing other things that will, by building these structures, that will, without doubt, hurt this gap, the thing I showed you, the 5/2 thing I showed you. And so it is a legitimate question and concern. All I'm saying, and I was being snarky because it was you, is that the reason is not because I don't think, and it is because I'm killing the gap by adding the screening wells because of that screening effect.
Mhm.
Anyone who knows better can correct me. I certainly don't. I'm not sure, but that's my instinct or hunch right now.
Yeah, I was just, thanks for the answer, nervous because things are all similar scales now, because you're like 25 nanometers offset for your screening. Your magnetic length is of order 10 nanometers. So, and it just seemed like all the numbers are going to get kind of similar.
They will, they will. And I have to think about it harder. That may be right, because I'm also going to be at lower magnetic field, and therefore the scale magnetic length is going to go up. So it could get closer. Of course, I can modify my heterostructure for in these screening wells. I'm not set at putting the screening layer at 25 nanometers. I don't even know if that's critical, so I could adjust that. And things get more interesting at 5/2, as Bob's in. Well, I think Bob was here earlier, so he's the expert. You're not at 5/2. What you're looking for, the signatures are not exactly the same, and so it may not even necessarily be true that I need this level of screening that I showed you. And you're looking at, well, essentially at 5/2, you can see something, at least in principle, that's associated with on and off of the interference pattern associated with the, whether you have an even or odd number of quasi-particles within the interferometer. So there, you could look at other signatures that don't necessarily need, and I'm not sure of this, but I'm thinking, may not need to have such strong screening that you're so deep in the AB regime. Not sure of that. Now, there's other signals that the interference pattern at 5/2 is complicated because there are other contributions as well. So it's actually you get many components. If you you look at Bob's experiments, you see lots of components contributing to the interference, but it's not even clear I have to do exactly the same experiment and have the same level of screening, or even that this level of screening is necessary. So there are modifications. I could change length scales in the heterostructure as well. But it's a good question, and it's certainly one I need to think about harder.
Are there other questions? We've gone a long time. We've kept Mike.
I have one quick one. Sorry. In the first paper result, you mentioned that you saw the jumps, and then you measure 1 hour after you saw the same jumps at pretty much the same locations. But then in later talks part, you were discussing gaps and temperature dependence, which maybe made me feel that it was more a statistical nature. And then also in your theory prediction, the jumps were kind of more evenly spaced. So I was confused that are the jumps, the locations of the jumps, are they like intrinsic, reproducible, or they're more sort of by chances?
I think there's a little bit of confusion there. Within a given, if you're talking about the phase jumps associated, what we think are adding or removing a quasi-particle in the central AB regime,
right,
at a fixed temperature and scanning magnetic field, they will, or gate voltage, they occur in the same location or repeat themselves all the time. That's not fluctuating. I don't know. Now, where they occur, I don't have full control over. That is fixed by the device. But once it's, and whatever changes in the potential, that may be true in the in that particular device. But once that device is cooled and in a given configuration, it doesn't change. So they're not statistical, I don't know, or what you're saying. They don't change. You go back and forth, and gate voltage over the full range of and the magnetic field over the full range, and they occur at the same locations within experimental resolution or close. And then their value of the jump is the same in their repeated measurement.
I see.
Now, if we're talking about something else where I actually, and that's even true if I raise temperature in the central region. What I was talking about in the other, when I go for big magnetic field excursions, and I see the decay in the oscillations and don't see the finite periodicity, that I'm attributing to fluctuations in a regime where I have a large quasi-particle number because I've made such a big excursion. And that has a different temperature dependence and changes, but they're not the same thing. I know I didn't explain that very well, but they're not, it's not the same physics I'm looking at, or they're different regimes, I should say. So there's nothing it's not noise, or the jumps aren't associated with random charge redistribution within the center of the interferometer, in the center of the plateau. Does that answer your question?
Yeah, that clarifies a lot. Yeah, thank you very much.
Yeah.
Any other questions? Okay, great. Well, so maybe we've tortured Mike long enough. So
that was great. I'm sorry for some of the incoherency of the talk.